morning and I was like, oh man, I can't believe it's only Tuesday. And then my family was like, actually, it's Wednesday. I thought, man, today's fantastic. It's the middle of the week, team. We made it. The sun is shining. We are sitting in the middle of our fourth week, and it's going well. I think it's going well. If you're just joining us, my name is Kobe Flatt, and for the next hour, I will be going through the MAP4C, our grade 12 Foundations for College Mathematics course. Every Monday to Thursday between 10 and 11 a.m., I go through the MAP4C course curriculum material. All of our courses here are 20 lessons, and you can do them independently. You can go through them at your own pace, at your own time, do what you can when you can. But for those that need a little bit more help, we do our radio Zoom classes. The radio Zoom classes give more in-depth explanations for a lot of the different course concepts. If you're following along on our radio Zoom, that means that you can see the screen that I have in front of me, which has our radio Zoom timetable. For term 1A, which is the term that we're in, it runs from September 2nd to October 31st. It's 9 weeks. We will be broadcasting a grade 12 college math. We have our PLAR English and our PLAR History Geography. We do a grade 12 college English. We do our new language course. We are offering Cree this term. We have the Ontario Literacy course. We've got the grade 11 college math prep course, as well as MCT4C. This is a grade 12 college math, but it's more specified. The MAP4C that I'm going through now is just foundations for college math. It goes over a little bit of everything. You can see in your booklet the table of contents, if you have your IL booklet, all of the different concepts that we will cover, all the topics that we go through in this course. Lastly, during this term 1A radio Zoom schedule, we have the environmental science. It's a grade 11 environmental science. If you would like to jump into any of those, it is not too late. Please reach out to us here at WASA. We can get you connected and registered, and you can start obtaining these credits. Now, that doesn't mean that you can't take other credits. If you need an elective and maybe you want it to be yes, I'm going to be a little bit of biased here and say if you want to take leadership and peer support, that's one of my classes, you can go ahead and take that now as well, but it's not being broadcast over the air until later on in our school year. So right now, these are the courses that we are presenting over the air and what we call our radio Zoom class. But you can always take the independent learning course if that is your preference. The other thing to note is, yes, our radio Zoom schedule is a 9-week term. But again, if something comes up, we understand that life happens and you might not be able to complete all that you had hoped for in 9 weeks. You might not be able to get this credit because something came up, you have to take off for a few weeks, and it's just too hard to get caught up. Don't worry, you can always roll over into the independent learning. Go work through the course material when you can, but know that resources are there for you and teachers are here for you. All of our classes are recorded and get posted to our WASA YouTube channel for you to check out at your convenience when you've got time. Today we are going to continue in our Unit 2 material. Yesterday we finished Lesson 8. So a quick recap, we talked about one variable data sets, how they give measures of one attribute, whereas two variable data sets give measures of two attributes for each item in a sample. We talked about correlation. We know that correlation is a relationship between two variables, and we first got to look at scatter plots, which represent two variable data points and may reveal a relationship between those two variables. Today we are going to further explore correlation through line of best fit. We will better understand linear relationships. Our learning goals for today are that we will be able to determine the equation of best fit, as well as be able to estimate and predict values through understanding the relationship between variables. Now, yesterday in our lesson 8, we talked about scatter plots, and I really built up to how we can represent visually different data collected. We talked about histograms and bar graphs and circle graphs, and then we ended with scatter plots, which was the focus of lesson 8. Because that is the foundation, our lesson 8 about scatter plots is a foundation for what we're going to get into in lesson 9. I want to go over to make sure that we have a solid understanding of what scatter plots are. Because we're going to go back and really dive into the concepts so that you are comfortable in knowing them, this lesson 9 is going to take us 2 classes. We'll do lesson 9 part 1 today, and we'll finish with lesson 9 part 2 tomorrow. So let's make sure we really understand what it is that we need to know so that we can build on it and be successful in the lessons to come. We learned yesterday that a scatter plot is a graph that is a series of points. We talked about coordinate pairs, we've talked about graphing, how to plot those pairs using our X and Y, and we did a few examples, not just in lesson 8, but previous lessons as well. We know that scatter plots represent two variable data points. We know that they may reveal a relationship between the two variables. We learned that in two variable situations, one variable may be dependent on another. So its value changes according to the value of the independent variable. We talked about an example being the value of a car depends on its age. I want to get into variables a little bit more today. We're going to build on so that when you have to graph your own, you'll recognize which is the dependent variable and which is the independent variable. So when conducting research, variables refer to characteristics that take on different values. So variables could be height, age, temperature, test scores. All of these are variables. Researchers often manipulate or measure variables in studies to test cause and effect relationships. These variables are known as dependent or independent variables. Let's look further at independent versus dependent. We touched on it yesterday, we alluded to it. Today I really want to make sure that we understand it so that we can be successful in the lesson 9 content material. When we talk independent variables, we're saying that the independent variable is the cause. Think of independent as cause. The independent, its value is independent of other variables in the study. So that's the cause. Now the dependent variable is the effect. Its value depends on changes in the independent variable. So the independent is the cause, the dependent is the effect. Cause and effect. That's what we talked about. These variables are known as independent and dependent. Researchers will manipulate or measure them to test cause and effect. Let's say that you design a study to test whether changes in room temperature have an effect on math scores. Here, we want to know if one has to do with the other. We're looking at which is the independent, which is the dependent. Is there a correlation? If any of you have ever had to take an exam in a gymnasium, you might instantly have that little shiver of, oh, I remember being crammed into a gym, all single individual desks, and everybody goes in. You have 3 hours to write an exam. You have to bring only your pencil with you, maybe a water bottle, and it's very intimidating. Not just the idea of having to sit for 3 hours or the pressure, excuse me, of having to write a test, but also you're in with a bunch of other classes, bunch of other ages, a bunch of other groups, and it's echoey because everyone's trying to be quiet, but then there's always that person that is fidgeting, and maybe you were that person. You're playing with your pen, you're scraping your chair. You go in, and there's a lot of other bodies, and so you're distracted. A lot of researchers want to know how to best accommodate student learning. There are actually people that get paid very well, a lot of money, to design and plan certain atmospheres, office spaces, playgrounds, classrooms. So if we can find out the best way to assist students in test writing, we'd like to know that. So we're saying that we have to design a study to test whether changes in room temperature have an effect on math test scores. Maybe it says something as simple as whether or not the student is comfortable. When you think or remember about going into this gym with a lot of other students, and at first it might be cold because it's big and empty, and you're freezing, and then halfway through the exam, all those bodies are moving and breathing, and it starts to warm up in there. Usually, going in to an exam, you want to layer up so that you can be comfortable, because if you're uncomfortable, it can really be distracting, aside from the noises and smells and whatever else is happening in that gym. Can something as simple as temperature have an effect? Let's look at it from the independent and the dependent variable viewpoint. Remembering that the independent is the cause, your independent then is the temperature of the room. You can vary the room temperature by making it cooler or warmer. So if we design this study, what we want to do is we want to vary the room temperature by making it cooler for half of the participants. And then the second group that comes in, the second half, we're going to make it warmer. That's going to be what we control to see if there is a correlation. So the independent is our cause. We're changing temperature. The effect then is our dependent variable, which would be the math test scores. You measure the math skills of all participants using a standardized test. That simply means that it's the same across the board. Standardized means everyone gets the same thing. So that's not changing. The temperature we're controlling, the temperature we're changing, but the test is staying the exact same. This way we can check whether the scores differ based on room temperature. Did those participants in the first half that had the cooler temperature being pumped into the room do better? Or did the participants in the second half, where the room was warmer, do better? We're looking for that cause and effect, where the independent is our cause, and in this example, it's the temperature of the room, and the dependent is the effect, which is the math scores. Yesterday, we did an example together, the one with Davis, who conducted an experiment comparing a person's leg length and how long it takes that same person to walk 100 meters. Davis gathered the data showing leg length in centimeters and time taken in seconds. When we did this together, we first focused on the parts of a graph. It's very important to have proper labels. We needed to have a title, and it doesn't have to be super creative or super fancy. Don't take a lot of time on it. It simply has to encompass what your research is about. So we needed a title. Then we needed to label the y-axis and our x-axis. You need to have those labels. The next part of a graph is to have a proper scale. Your scale should cover the content of your data. If all of your data takes place in the let's say 40 to 90 range, we don't want to go up by ones if we're talking about labeling our y-axis, because then all of our data will be way at the top and it'll all be clumped together and we won't get much out of it. You want an appropriate scale. So if all of our data is in the, what did I say, 40 to 90s, 40 to 90s, we want to make sure that we can accurately show what it is that we're trying to represent. So you might do that fun little break in your graph to show that now we're starting at 30, and then maybe if we're going up to 90, we want to say maybe we're doing 30, 35, 40, go up by fives. That's going to help. And then your x-axis, you can do the same thing. Make sure it's encompassing what needs to be. So if we actually take our example here from Davis's experiment with the leg length, remember yesterday we did that break and our x was at, we started at 50 and then we went to 55 and then we did 60, we went up by fives, and we did the break on our y-axis because the smallest y was 62. We started at 60 and we went up to 84 and we went up by twos. You want that appropriate scale. Once we did that, we started to plot our points. So I've gone online to show what we did yesterday. And then we had to look at, does the graph suggest a relationship between? That's looking for correlation. Does the graph suggest a relationship between leg length and time taken to walk 100 meters? And if so, we had to describe the relationship. So we looked at finding the shape of our data and seeing if it pointed to one slope or another. We saw this negative correlation that says the longer your legs are, the shorter the time to walk 100 meters because you're taking longer strides. So it made sense. Lastly, we wanted, oh, did I not just do that one? Here showed a better, more zoomed in so that you could see how it looks. C said use the scatter plot to estimate the time it would take a person with leg length 85 centimeters to walk 100 meters. This was alluding to today's lesson material. We drew a line that went through the majority of our data points so that we could go up 85 and over to find that it took about 63 seconds. That line is called the line of best fit, and that is what we are going to get into today. But making sure that you understand cause and effect relationships, knowing that when you're observing a relationship between two variables, it does not necessarily mean that one variable causes a change in the other. There are other factors that could be involved, or the correlation could simply be a coincidence. When we looked at the last part of yesterday's example of how might Davis make the results of his experiment more reliable, we talked about having a larger range because always the more data you provide, the more accurate and the stronger your relationship will be. But we didn't want to just take anybody. If you think of typically people with shorter leg lengths are children. So there is a difference in a 50-year-old man walking 100 meters and a 5-year-old boy walking 100 meters. We wanted to try to keep age the same, gender the same, body type the same, the athletic ability the same. So just because you can see a relationship, it doesn't necessarily mean that one caused the other. There could be other factors involved. Demonstrating cause and effect conclusively is a very challenging task, and it requires careful analysis and specialized statistical tools. Yesterday, I used some vocabulary that I told you we were going to get into further, and that's coming up in today's lesson. We are going to hear the word outlier again in today's lesson. An outlier is an observed value that differs markedly from the pattern established by most data in a set. You're going to see how there's going to be sometimes these pieces of data that it's like one of these things is not like the other, and that's an outlier. It's an observed value that differs markedly. We're also going to be talking about linear correlation. We're familiar with linear models and relationships. We know how to identify them in a graph, in a table of values, in an equation. A linear correlation is a trend where points may lie in the general direction of a line. We know that linear is that straight line. Now, linear regression is the process of identifying a line of best fit for a set of data. And that brings us to page 27 of your IL booklet. Line of best fit is simply a line that passes as close as possible to a set of plotted points. It can be drawn through data points to best represent a linear relationship, that straight line, between two variables. Now, this line is also known as regression line or trend line. In today's material, if we get to it today, depending on, we might get into it part 2 most likely, that regression line, we're going to be looking at what that is, what it means, the strength of it, so stay tuned for that. Let's practice this line of best fit. We know what it is. We know it's drawing a line through your data to see if there is a correlation. What does that look like then if we are making one on our own, much like we did with Davis's experiment? We have our scatter plot. And now that we know that a line of best fit is a line that passes as close as possible, we understand that we're not going to get all of them. We're not playing connect the dots. We just want to get as close as possible all the data points. So you want to, even if there are ones, if you're following along with our Zoom slides, you can see on the board in front of me that I have a scatter plot for the experiment that Davis conducted. You can see that we have this beautiful, almost perfect straight linear line, but we have these other data points that are kind of hanging out. And yes, you could have that straight line. You could also make your line so that it's a little bit more accurate. We can go kind of close in between. If you're following along, my blue line is my more accurate line of best fit because it's representing more of the data points. It's including these 3 data points in my upper right quadrant. And then, as I said yesterday while we were doing it, I have this lonely little data point that is, it looks like it is 64 and 63. He's my outlier. He's not really with the group. He's not part of the tight grouping, but he still matters. We have to include all of the information because it's all relevant to our study. We don't want to sway a study one way or another, and we're going to get into bias here in our lesson. In our course, right now, our line of best fit is going to pass through as many data points as possible. So we're looking at creating a line of best fit that takes all of the data sets into account. Let's look now at how that can be represented more accurately than just me freehanding a straight line on the board. You are all familiar with Desmos scientific calculator. It's the one that we use as we go through questions here. Today I'm going to introduce you to a new Desmos tool. Desmos has a graphing calculator that is absolutely lovely in finding line of best fit, which we're going to get into today. It's a great way to also check and make sure that you're on the right track with your graphs. It's so important to know how to do math, mental math, and without a calculator and without tools and equipment. But it's 2025 and we have those tools and equipment available to us. So, I'm all about working smarter and not working harder. But do know you should have those basic foundations of how to do it should those tools disappear. If power goes out or for whatever reason you don't have access to it. We've done the line of best fit through our scatter plot. Today I'm going to show you how to find line of best fit on the online Desmos graphing calculator. If you're following on Zoom, we have the practice question of Naomi on the board. Naomi researches the cost of houses in a new area. She is looking for a 2-story detached house, asking prices of $300,000 or less. She wants 2,000 square feet of living space. So these are her conditions. This is what she would like to have. The question asks us to graph the data. Now here it's telling us use axes that show house sizes up to 2,500 square feet and prices of up to 400,000. So I am going to show you how to do this online. I'm going to put it over here. When you are in your search engine, you can type in Desmos, and usually, hopefully, typically, the first one that comes up is Desmos, beautiful free math. And then we have multiple options. We have graphing calculator, scientific calculator, graph, 3D graphing calculator, 4-function calculator. We've always clicked scientific calculator because that's all we need to do all of our calculations in this course up to this point. Today, we're going to click on graphing calculator. And graphing calculator is going to bring up this beautiful graph. I'm going to put them side by side on my screen here so that you can follow along. And you'll see we have this Cartesian plane. We have this graph paper, this grid that we've been working with the last few days. On the left-hand side of our Desmos graph, we have this toolbox, this dialog box. And right now it just has a blue number 1 highlighted in a box and ready for us to type in whatever we want. What we're actually going to do is we are going to go over to the left where there's a plus icon, a plus sign, and it says Add Item. We're going to choose Add Item, and we're going to scroll down to Table. Much like we did in our lesson of trying to input variables to graph our different line, we were in lesson 6, I want to say. Does that sound right? Nope. Lesson 6 was all about exponents. Lesson 7, we were in lesson 7 because we were doing linear, quadratic, and exponential functions. And we learned how to do trial and error. We put in a table of values, -3 to +3, and then we substituted what would y be if x was -3, -2, -1, 0, etc. We are familiar with our table of values. That's all we're going to do today. We're going to create our own table of values in an online tool through Desmos Graphing Calculator. Here we have the 7 different houses that Naomi found. We already have a table that says she found one house that had 1,700 square feet. The price of that house was $271,900. Our size was always listed as square feet, and our price is listed in dollars. What we want to do is we want to graph this information. Yes, we can do it by hand for sure, and we know how to do that because we've done that with different examples leading up to. Today, we're going to put it online. Our size is going to be our x-axis. Remember, you always plot x and then y. In the table of values that you have on Desmos Graphing Calculator, in x, we're going to write 1,700. Now you can hit enter or you can hit the down button, and we're going to put in the next x value of 1,850. Hit enter. Now Desmos thinks it's being helpful. It thinks that it knows what we want next, and it put 2,000 in for us. That was kind, but that's not the pattern that we're going with. We're simply inputting the 7 houses that Naomi researched. So I'm just going to type right over top that 2,000. I'm going to put in 1,600 and hit enter. Then her next house she found was 1,650 square feet. Then she found another 1,700 square foot home, a 1,800 square foot home, and a 1,550 square foot home. The price now is our y value. So for the first 1,700 square foot home that Naomi found, the price was $271,900. I'm going to hit enter to put in the corresponding price with the size of the home that she found. So for 1,850 square foot home, it was $289,900. Then it was $277,900. For the 1,650 square foot home, it cost $289,900. For the second 1,700 square foot home, it was $279,000. Then the 1,800 square foot home was $294,900. And the last house of 1,550 square feet, it was $269,900. We have input all of our data points. We have the size of the house with its corresponding price. If you look to the right where my graph is, you don't see any of those plotted points. We put in the information, it should be showing up on our graph, but if you look at our scale, you'll see that all I have within my window is an x-axis of -10 to +10 and a y-axis of -10 to +10. But my plotted data points are nowhere near that single digit range. We're looking at 1500 to 1900 range. So if you go over to the right, where in the top right corner there's a zoom in, a plus button, and a zoom out plus button. If we were to continually click this zoom out button, we would hopefully eventually come to find, there they are, ta-da, these teeny tiny plotted points way up near the 300,000 range. Now with the button on my mouse, I'm just going to scroll in, or I can push the plus button to scroll in, and you'll see all my data points seem to be in this completely straight line, which we know isn't accurate, and that's because my scale is not ideal. This is why having an appropriate scale is so important. Rather than zooming in, zooming out, shifting, manipulating my graph by clicking on it and moving it around, there is an easier way. Going up to the right-hand corner, there's a wrench icon that says Graph Settings. I want to click the Graph Settings, and I want to look at my x-axis and my y-axis. And I can label it. So my x-axis can be labeled size, and always include your unit of measurement, square foot. The y-axis can be labeled as price. Again, always include your unit of measurement. I'm talking dollars. Now, the x-axis, if I'm looking at my x-axis, I can see my smallest one is 1,550, and my largest one is 1,850. But if you look back to our practice question, it says use axes that show houses up to 2,500. So even though my largest house is 1,850, it wants me to go up to 2,500. And we can do that, that's fine. So I'm going to highlight the x-axis where the lowest is going to be 1,500 up to 2,500. And you can see that my graph has already changed once I input its new parameters. The the y-axis now, if we look at it, my cheapest house seems to be 269,900. So I'm going to put in 260,000, and if I look back to my practice question, it says use axes that show prices of up to 400,000. So I'm going to put 400,000 in my what it should go up to. And now I can see that I have a way more accurate scatter plot where it's not all in a straight line vertically. You can see now I have more of a data cluster, a gathering here. And there are my axes labels. I have price on my y-axis and I have square foot on my x-axis. So I have graphed the data. I have showed houses that Naomi researched and included the parameters that it's asked for, with the axes going up to 2,500 and 400,000. Now, part B, so here's what I had. Part B says Naomi's researching the cost of houses in new era. Yep. Now, describe any trend that you see in the graph and draw a line that you think comes closest to matching the trend. Thinking of the line of best fit and how it needs to pass as close as possible to a set of plotted points, we are going to draw a line that is our line of best fit. So I'm going to draw essentially through the middle because I have an accurate representation on both sides. Describe any trend you see in the graph. Well, I can see that there is a positive correlation. It's moving up and to the right. Because it's moving up and to the right, I can say that we have a positive correlation that as the larger the house gets, as houses increase in square footage, they will also increase in price. So the bigger the house, the more money it's going to cost, is what it essentially boils down to. When you are describing trends, you want to be specific. You want to say that there is a positive correlation. You want to say that it's moving from bottom left to top right. You want your line of best fit to pass as close as possible to a set of plotted points. You want to try to get as many data points as possible. We looked at how when you zoom out, it's really easy to draw a line. I'm going to go back to our Desmos graphing here, that if I zoom out, oh look, it's a perfect little cluster, one melded dot, and I can easily put a line through there. But as you zoom in, there again, we can put a nice line through the tighter cluster, and the more I zoom in, the more spread out my data becomes, and it does get a little bit trickier. So you try to go through as many points as you can. So if I'm actually using the Desmos graph that we created, I typically want to try to connect at least 2 data points. So the one through the middle, I might try and connect like so. If you're following along on Zoom, you'll see that I have connected 2 of my data pairs, my coordinate pairs, my plots. That's through the middle and encompasses the majority of my data sets. Now, line of best fit is picking 2 points that represent the general center of the points plotted. You want to draw the line of best fit through those points, generally dividing the plotted points even on both sides. So you can see I have 2 to the left of my line of best fit and 3 to the right. I've tried to include as many as I can to make them even on both sides. The next part of our lesson is to find the equation for the line of best fit. There are a few ways to do this. I'm going to see if I can get back into my... Here we are. Just to reiterate, the slide that I've opened in front of me, drawing the line of best fit, involves more than just finding a pathway through the middle of the data. It's the line that is closest to each point. The more varied the position of points, the more difficult it is to draw the line of best fit. When they're cluster tied together, it's a lot easier. When they're varied, it becomes more difficult. Because we went through a lot of technical how to do it on Desmos, I do want... Oops, I don't know what I just pushed. Uh-oh. I somehow went all the way back to the beginning. That's okay. I want to show you our WASA YouTube channel so that if you need to, you can go back, watch this class again, and then you can pause it and try it yourself. Try inputting the data points from Davis's experiment back in lesson 8 with the leg length. You can try and plot the support questions from lesson 8. Play around with it. See what you can come up with for finding how to use a table of values, how to graph a scatter plot, and then how to input a line of best fit. You're going to go to YouTube. You can type in WASA Distance Education Center, and you will get our YouTube channel. And it should look like this. It should have WASA's logo. It should have the front of our building, the red-sided building with our WASA sign. If you find that logo and the front of our building, you'll know you're on the right YouTube channel. WASA Distance Education Center has different playlists. The playlists are the different classes. I showed you at the beginning of class all of the classes that we are offering this term, and they are all listed here. So you can go and find our LNCAO, the PLAR History, the PLAR English, the Ontario Literacy course, and our MAP4C Foundations for College Mathematics course. You can click on MAP4C, and listed to the right of the playlist are all of the classes we've done so far. We have Class 1, the Introduction, Unit 1, Lesson 1, Part 1. We have the lessons on the right. So if we click on, we just did Lesson 8 was our last class. And then you can go down to the description and you can see what each class is about. So if you're not sure, was it in Lesson 8? Well, Lesson 8 talked about scatter plots. We explored scatter plots and how to use them. We compare scatter plots to other graphs to better understand correlation through reading data. If you are looking at Lesson 3, for instance, and you know that it took a few classes, like our Lesson 7 took a few classes, you can go through and see, okay, Lesson 3, Part 2, we practiced calculating mortgage costs through the use of present value formula. We now understand the cost of borrowing through a mortgage. It helps you to pick exactly the one that you need that extra help with. So it's all there on our YouTube channel, and it really is useful for slowing things down, pausing, rewinding, going back to make sure that you understand. So feel free to do that for this lesson. Again, open up a new graph. You want to go to Desmos, make sure you're clicking on the graphing calculator this time and practicing, how did we input that table? We're going to go up to the left-hand side, we're going to click Add Item and scroll down to Table. And then I do encourage you, go and look at the Lesson 8 information and you can put it in there. Let's practice creating a graph for the scatter plot of, here we have on page 22 of Lesson 8 of men's times. We're going to put the year on the x-axis, so our x is the year, and the times on the y-axis. So in the x, which is our year, we put 1981, and the time that corresponds is 11.82. The next year is 1982, and you can do it that way, or we can do 1983, then 84, then 85. And this is where it's beautiful to just hit enter because Desmos is going to input it for you. It's thinking, oh, I think I know where they're going with this. And with Naomi's house hunting, it didn't. I mean, it was nice that it tried. But here for the men's times, it is super helpful because we're going to go all the way to 1995. So we didn't have to do a whole lot of work. We just had to hit enter. And now we're going to put in the times. We're going to put in all of the corresponding times into the y-axis that align with the years in our x-axis. And I'm going to try to do it a little bit quickly here before we run out of time. But even if we do, you can still see where we're going with it. And I might only make it to 1990. And that's okay. We'll just delete the other one so that you can see the data points should be showing up on the right side of our graph, and I don't see them. Remember, that's because of your scale. If you were to move and zoom out, our X starts at 1981, so we have to go all the way to 1981 before we see, there they are, way down here in the bottom right, all clustered around the 1980s, 1990s. You can zoom in, or you can use your wrench icon to adjust the graph settings. And then practice drawing your line of best fit, seeing is it positive, is it negative, is there no correlation. Here there is a beautiful line. It's not scattered all over like the house hunting of Naomi's research. So practice, go through, find different, you can even do the key questions from lesson 8 as a way to check your work. Did you create the scatter plot correctly? Do your clusters look like the ones presented on Desmos? Don't rely solely on that if you're not super confident and familiar with how to work and create graphs on Desmos, but do use it as a guide, as a gauge if you need to. So that's all there for you. Tomorrow we are going to finish lesson 9 and we're going to look at the equation and calculating a line of best fit. So please tune in again tomorrow, but enjoy the sunshine today. Have a lovely rest of your day and we'll see you back tomorrow.